A brief overview of Rapita Systems. We are tool providers for on-target software verification for critical systems. We have two offices, one in the UK and one in the US. We were founded in 2004 as a spin-off from the University of York. We're owned by Danlaw Inc. and we have distributors all over the world where we serve lots of customers, primarily in aerospace, but also in the automotive domain as well. In terms of our product offering, the core of that offering is RVS, which includes RapiTest for test authoring and management, RapiCover for full code coverage up MCDC level, and the two we'll be looking at in more detail today are RapiTime, which is for on-target timing analysis, and RapiTask, which is for task visualization. We'll also be touching today on Cast-A2A compliance package and the RapiDaemons interference generators. So that's a little bit of background about Rapita Systems. So from there, I'll pass you over to Mike Horgan from DDC-I, who will be introducing DDC-I and the tools.
All right, thank you, Nick. Good data. Thanks to all for joining and welcome to our webinar discussing an out-of-the-box solution for multi-core analysis. My name is Mike Horgan. I'm a technical marketing manager for DDC-I. I'm based out of Denver, Colorado. DDC-I, based in Phoenix, Arizona, has been a leading worldwide provider of mission safety critical software for over 30 years, and our primary market, certifiable avionics software. So let's get started. For any DO-178C certification, you're going to have to provide evidence of analysis for timing and structure of your system software and design. If you've done safety critical before, you've done these analyses and provided the appropriate artifacts. Today, we want to discuss the analysis of worst case execution time in the multi-core environment, identifying and mitigating interference patterns that affect the to have disastrous results. For business reasons, minimizing the worst case execution time allows for more functionality. Well, in our avionics market, the FAA has formalized the position on these analysis, especially with regards to interference patterns, which affect your worst case execution time in a document called CAS-32A. The document provides guidance, generally taking the form of, did you consider this in your multi-core environment while you're addressing the DO-178C objectives? Stating that more precisely, auditors are going to ask, how are you going to manage your interference patterns and your resource contention while you're using multi-core? Highly recommended to get this document as soon as possible and evaluate for all your projects. And remember also, these certification efforts are a cooperative effort. You're going to have to address these concerns and your objectives with your COTS vendors, with your tool suppliers, and with the certification authorities. So the sooner you start coordinating, the better. Discussion today will be on the features that support meeting the objectives of the interface channels and resource usage, error detection and handling, and the safety nets. Additionally, for software verification, you're going to have to provide these analyses, so you're going to need tools to measure the effects of the features that you implement. Okay, to set the stage for the descriptions about the features and the tools available, let's take a look at the high-level Deos architecture. Deos is a fully modular microkernel architecture. The Deos kernel, depicted in purple here, is a module that is dynamically linked at runtime with all your other components, all your other software, to provide the functionality of the system to meet your system requirements. The binary Deos registry, depicted in orange, is the set of rules for space and time partitioning established by your integrators. Items like how much memory a partition is allocated and how much time an execution unit gets to run are represented in this binary. Using this registry, the Deos kernel enforces the rules. The partitions in dark blue represent a single address space for space partitioning enforcement, and then integration of the execution units within a partition, whether they're Deos threads or 653 partitions or POSIX P threads, support the time partitioning enforcement. RTOSs have to provide the ability for multi-core developers to eliminate and bound the resource contention, especially in those high impact areas like cache, memory access, device buses, for example, a PCI bus. RTOSs must also provide these features in such a way that the current execution is a performance advantage. Simply eliminating or bounding interference, it's definitely not sufficient. The result has to perform at least as well as a single core solution. And ideally, if you're using multi-core, it's got to perform better than a single core solution. A combination of space and time partitioning mechanisms will be needed to address the various interference and performance issues. And safety nets as a last resort will be needed as well. Let's briefly talk about the RTOS features first, then we'll proceed to the main webinar topic of identifying and measuring the effect of the interference mitigation strategies in the DS environment using the Rapita toolset. Here are the set of features that address CAS32A concerns related to interference patterns and shared resources in the DOS environment. First, we have our safe scheduling. This is a bounded multiprocessing feature that allows the integrators to align the execution units, the threads, the 653 partitions or POSIX partitions, to minimize shared resource contention. Then we have memory pooling and cache partitioning. Cache and memory contention are the biggest hitters in the multi-core environment for performance, and thus a major concern. The integration strategy here is to minimize the cache misses. Also, if you're minimizing those cache misses, you're mitigating some of the memory bus contention concerns as well. These first two items are proactive integration solutions. CAS32 indicates you must detect and control poorly behaved applications, while safety nets are a reactive, on-target, platform-dependent software strategy to meet that goal. These are based on hardware-software interfaces available for monitors in the system. Additionally, you're going to have to defend all of your mitigation strategies. Keep in mind, again, this is a collaborative effort. We will defend our products and our strategies in any audits that you encounter. Okay, so let's start out with DOS safe scheduling. Timeline is broken up into windows. The number of windows, the length of windows are configured by your integrator to meet your system requirements. The window boundaries are identical on each core. We're showing two cores here, but the windows and the multiple schedulers that you see are applicable to a single core. By spanning the cores and the window boundaries, you get to define what schedulers can operate concurrently. And of course, you define what is actually executing in the context of each one of those schedulers. So let's think about that with regards to resource contention. By placing the use of a resource in different windows, you're controlling the use and contention. A simple example, you have a serial device output that you execute in core 0 on window 1, and then you execute that output again in core 1, window 2. You've separated them in time, you've separated them by cores, you are controlling the resource contention in use. Think about this as well with regards to previously developed binaries, software that you've set up for other programs. You're reintegrating to get multi-core efficiencies. You're not doing a full redevelopment. You know your applications. You can decide what can run concurrently. Example, you have a memory-intensive application versus a compute-intensive application. You could possibly run those in the same window on different cores to get some of the multi-core efficiencies. Note also here that we have multiple schedulers, the RMA, rate monotonic analysis, which is the DOS default, ARINC 653, and POSIX. The integration of these across the timeline is totally possible. This setup with the timeline also allows for mixed criticality application integration as well.